This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 14, Quantum Mechanical Postulates. There are 6 quantum mechanical postulates. Section 14.1. The physical meaning associated with the wave function is probability. Every particle in the universe is a wave that can be described by a function, the so-called wave function, psi of r and t. R is a vector. It specifies the position of the particle. T is time. If we multiply the wave function by its complex conjugate, we will get the squared modulus of that wave function. If we multiply the squared modulus of the wave function with d tau, we get the probability of finding that particle within this volume element d tau. D tau is dx times dy times dz. And again, this is the complex conjugate of the wave function psi. And also, this can be obtained by multiplying the wave function psi by its complex conjugate. So now, what is a complex conjugate? You simply replace every occurrence of I in this psi to get psi star, the complex conjugate. For example, if you have a function e to the power of ix, its complex conjugate is e to the power of negative ix. If we are looking at a particle in a one-dimensional world, we do not have to use the three-dimensional vector r. We'll just replace this vector r with x. X is the position of this one-dimensional particle. And then the probability of finding the particle between x and x plus dx at time t is this. Again, it's the squared modulus of psi times the volume element dx. The volume element in a one-dimensional world is simply dx. At any time t, if we integrate the probability of finding the particle between x and dx, the result is 1. The physical meaning is very simple. There's 100% probability of finding the particle from negative infinity to positive infinity. Again, psi star is the complex conjugate of psi. One just replace every occurrence of I in psi to get, or with negative I, to get its complex conjugate. Again, this I is the square root of negative 1. Another example is this. This is a function of time. So e to the power of negative I, et over h bar is our function. Its complex conjugate is simply replacing this I with negative I. And then we have negative I. Two negatives make a positive. The complex conjugate of this function is this. The complex conjugate of a real number or function is itself, because there's no I in a real number or function. Now let's look at postulate 1. The wave function must be single-valued, continuous, and finite. So this is not a good quantum mechanical wave function. It's not single-valued. For example, when x is 2, this function value can be 4 or negative 2. Again, this is not single-valued. This is a violation of quantum mechanical postulate 1. This one looks good, but it's a quadratic function. You have to imagine when x approaches infinity, the function value approaches infinity as well. So this function, this quadratic function, is not finite. Again, this function is also a violation of postulate 1. Section 14.2. Every observable has a corresponding operator. What does that mean? In the physical world, anything we can measure is observable. For example, the position of a particle or the momentum of a particle. Postulate 2 states that for every observable in classical mechanics, there exists a corresponding operator in quantum mechanics. So we have the first column that includes some observables: the positions, the momentum, kinetic energy, potential energy, total energy, angular momentum, etc. The second column is the symbol of those observables in classical mechanics. For example, the position, x, y, z. Momentum, px, py, pz. Px is simply the mass of the particle multiplied by the velocity of the particle in the x direction. Kinetic energy, potential energy, sometimes we use Ke or Pe for kinetic energy or potential energy. And then total energy, usually we just use E. Angular momentum, we usually use L. L is a vector. It has 3 components in the x, y, and z directions. Now the operator in quantum mechanics. For positions, you simply put a little hat, a caret, on top of x, y, z. You also put a little hat on px, py, pz to specify that this is now a quantum mechanical operator. Same treatment here. For the total energy, we do not use E, we use H by convention. H stands for Hamiltonian, but the physical meaning of H is the total energy. Angular momentum, we use Lx with, again, a little hat on top. Same here. Operation. So, an operator can be applied to a function. And what is that kind of operation? If you apply this x operator to a function f, the result is x times f. If you apply the y operator to a function f, the result is y times f. So this is pretty simple, right? These operations are simply multiplications. However, if you are looking at the momentum operator, it's different. If you apply this px operator to a function, the operation is to apply this operator to that function. So essentially, if you apply px to a function f, the result is negative I h bar times the first derivative of f with respect to x. Same here. If we apply this py operator, the momentum operator in the y direction to a function g, and then we have negative I h bar delta g over delta y. Same here. Kinetic energy. Well, it's also complicated. The kinetic energy operator in the x direction is negative h bar squared over 2m times delta squared over delta x squared. Similarly, you have the same coefficient here multiplied by second derivative with respect to y and z, and you sum up the kinetic energy in all 3 directions, you get the total kinetic energy operator. H bar is the reduced Planck constant. H bar is h over 2 pi. H bar is roughly 10 to the power of negative 34 joule per hertz. M is the mass of the particle. Potential energy operator. Well, sometimes we write this E sub potential as the potential energy, but very often we use a single letter V to denote the potential energy. So if you apply the potential energy operator to a function f, the result is V times that function f. Again, it's a simple multiplication. For example, if your potential energy is cosine x, all right, and then you apply this cosine x operator to a function f, the result is cosine x times f. Total energy operator, this is H, not E. So this H is simply the sum of the kinetic energy operator and the potential energy operator. So you can see this is the kinetic energy operator plus the potential energy operator. Just a reminder, over here we are looking at the sum of the kinetic energy operators in the x, y, and z directions. Therefore, we have three terms. And if we look at the potential energy operator, it depends on x, y, and z. Now, angular momentum. Angular momentum is a vector in the three-dimensional world. It has three components, Lx, Ly, Lz. The corresponding operators are simply this caret on top of L sub x. And what's the operation? This again looks a little complicated. It's negative IH bar times y delta over delta z minus z times delta over delta y. So if we apply this Lx operator to f, what's the result? The result is simply this. This is when we apply Lx to f, you get this expression. You have to evaluate the first derivative of that function with respect to z, plug in here, and same here. And then you do a subtraction, and finally you multiply the difference by negative IH bar. All right, so now I'm going to return this expression to the operator. This is an operator. An operator is neither a function or a number. An operator can be applied to a number or a function to generate a new number or a new function. Now let me show you the classical angular momentum. So again, angular momentum is a vector. In classical physics, it's just the cross product of r and p. R is the position, p is the momentum. And R cross product p can be written as this 3 by 3 determinant. I, j, and k are the unit vectors in the x, y, and z directions. X, y, and z are the position of the particle. Px, py, and pz are the momentum of the particle in the x, y, and z direction. If you are familiar with determinants, you know we can decompose a 3 by 3 determinant into 3 2 by 2 determinants, 3 of them. How do you do that? You just copy I here, j here, and k here, the 3 elements in the first row. And then I, j, and k should be multiplied by a 2 by 2 determinant. So after this I, we need to have this y, z, py, pz determinant. After this j, we need to write x, z, px, py determinant. After this k, we have x, y, px, py determinant. And for the first and third and fifth, in case you're dealing with 5 by 5 determinant components, we have a positive sign. And for the second, fourth, etc., 2 by 2 components, we have a negative sign. All right, so we have plus sign and negative sign alternately. And we can just simply evaluate a 2 by 2 determinant. It's y times pz minus z times py. Over here, it's x times pz minus z times px. And therefore, we can expand this L to be this I, the unit vector in the x direction, times ypz minus zpy. And then j times this zpx minus xpz, and then this k vector, the unit vector in the z direction times xpy minus ypx. This is a review of decomposing a 3 by 3 determinant. If I have a 3 by 3 determinant A, B, C, D, E, F, G, H, I, we can also do this operation to determine the final expression of this 3 by 3 determinant. So one way to do this is to copy the first column here, the second column here, and then we draw this 3 lines, diagonal lines, the red lines. They're going to be the positive terms. So this line is A times E times I, this line is B times F times G, this line is C times D times H. Those are positive terms. And then we can draw this 3 blue lines. C times E times G will be negative, H times F times A should be negative, I times D times B should be negative. So we have a total of 6 terms, 3 are positive terms, 3 are negative terms. Or you may find this kind of expression, especially if you have learned linear algebra. If we have a 3 by 3 matrix, you usually see those kind of subscripts, 1, 1, 1, 2, 1, 3, to indicate the first row, column 1, column 2, column 3, the second row, and then column 1, column 2, column 3, the third row, and then column 1, column 3. And similarly, you just copy the first column, 1, 1, 2, 1, 3, 1 here, and then the second column, 1, 2, 2, 2, 3, 2 here, and then you draw 3 red lines, diagonal lines. They are parallel to each other, and they are the positive terms. So the product of these 3 elements should be positive. The product of these 3 elements should also be positive. The last positive product is here. And then you need 3 negative products. In the end, a 3 by 3 determinant always contains 3 factorial terms. That's 6 terms. Half are positive, half are negative. N by n determinant always contains n factorial terms. Half are positive and half are negative. Section 14.3, the result of an individual measurement. Postulate 3. In any measurement of an observable associated with operator A, the only values that will ever be observed are the eigenvalues lowercase a, which satisfy this A operator. B applied to psi is equal to this lowercase a times psi. So when you see this kind of equation, as long as this lowercase a is a constant, we say this psi, the wave function psi, is an eigenfunction of the operator A. This lowercase a is the corresponding eigenvalue. It's extremely important. So let's say we are looking at the momentum operator. Let's say this A is the momentum operator of a particle. To make it a little easier, let's imagine a one-dimensional world. So this momentum operator is simply px operator. If you try to measure the momentum of that one-dimensional particle, the only value you will ever observe is the eigenvalues of the momentum operator. So how do you get those eigenvalues? You need to find the eigenfunctions of that momentum operator first. So it gets complicated. Basically, you are given an operator first. It could be the position operator. It could be the momentum operator, right? It's just any operator that corresponds to a physical observable, any operator. Your job is to find all possible eigenfunctions of that operator. For each eigenfunction, you should be able to determine its eigenvalue. And that eigenvalue is the possible value you will ever be able to observe. All right? So again, this is very important in quantum mechanics. In quantum mechanics, if we are trying to get the value of the momentum of a particle, we do not actually measure its velocity. We do not have to. We simply get the eigenfunctions of the momentum operator, and then we determine the corresponding eigenvalues A. And then we predict the value of the momentum of that particle will be one of the many eigenvalues here. All right? Sometimes if you know more about a particle, you know the eigenfunction of the particle, and you know the wave function of the particle. And if you are lucky enough that wave function of the particle happens to be one of the many eigenfunctions of the momentum operator, congratulations, you will be able to predict the exact value of the momentum of that particle. Again, let's say you have a particle, you know its wave function, and that wave function is one of the eigenfunctions of the momentum operator. Congratulations, you will be able to predict its momentum exactly. All right? But that's not always possible. Very often, the wave function of a particle is a combination of many eigenfunctions in this form. So again, you imagine a particle. It has a wave function psi. And this psi is not an eigenfunction of the momentum operator. However, we can express that eigenfunction in terms of this, a sum of the weighted psi sub I. And each psi sub I is an eigenfunction of the momentum operator. So that's possible. Let me give you one analogy here. If you have just any smooth function, you can expand it as a infinite series of polynomial functions. That's so-called Taylor expansion. We have a similar idea here, but we are not using, a constant x to the power 1, x to the power 2, x to the power 3 here. We are using the eigenfunctions of the A operator here. So we're going to combine the eigenfunctions of the A operator, or in particular, if we're looking at the momentum operator, we are doing a linear combination of these eigenfunctions. All right, so we can expand any smooth function, any single-valued, continuous, and finite function to the sum of the, to the linear combination of the eigenfunctions of the operator. All right, and this n can be infinity. This n is often infinity. We often need to do a linear combination of infinite number of eigenfunctions to describe a particle. What about this C sub I? C sub I is the coefficient of psi sub I. So again, if you have a particle with a wave function as the linear combination of the eigenfunctions, and then if you try to measure, for example, the momentum, the result is going to be one of the eigenvalues, A sub I. All right, so look, we have a linear combination of the eigenfunctions of the momentum operator. So the eigenfunctions can be psi sub 1, psi sub 2, psi sub 3, psi sub 4, etc. So if you try to measure the momentum of such a particle, the result will be either A1 or A2 or A3 or A4, etc. A1 is the eigenvalue of psi 1, A2 is the eigenvalue of psi 2, A3 is the eigenvalue of psi 3, etc. We just don't know which value will come up However, we do know the probability of observing a sub 1, a sub 2, or a sub 3. It's actually c sub 1 squared, c sub 2 squared, c sub 3 squared. So this c sub I itself has no physical meaning, but if you take the squared modulus of this coefficient c sub I, this is actually the probability of observing the eigenvalue a sub I. Okay, now again, if you have a particle, you know its wave function psi, alright? And then it's your job to expand it into a linear combination of the eigenfunctions of the operator of interest. In general, we're going to say, well, just the A operator, alright? And then if you try to measure the value of A, you will get one of the many eigenvalues, alright? It can be A sub I, A sub 2, A sub 3. Which one we don't know. It's probabilistic. And what's the probability? It's just c sub I squared. If c sub I is a complex number, well, we'll have to say it's the squared modulus of c sub I. This is the complex conjugate of c sub I multiplied by c sub I. Alright? Okay, but it's more interesting if you make a second measurement. Let's say you do a first measurement. We don't know what the result is. It can be A1 or A2 or 3 or A4 or any other eigenvalues. Let's say you got A4, A sub 4. Then you do the second measurement. It's going to be A sub 4. Again, the third measurement, it's going to be A sub 4 again. So if you repeat the measurement of A, you will keep getting A sub 4 after the first measurement. If you get A sub 5 in the first measurement, then the second, the third, the fourth measurement will all give you A sub 5. Well, what's the reason behind this phenomenon? In your first measurement, you have the wave function of the particle, which is psi, which is a linear combination of eigenfunctions. But after the first measurement, this psi collapses into one of the many eigenfunctions. So in case it collapses into psi sub 4, your measurement will result in A sub 4 as the eigenvalue. And after that, the wave function of that same particle is going to be psi sub 4. It's always psi 4. So you can just keep measuring its value. It's going to be A4 always. Again, the first measurement is going to be probabilistic. After that, it's going to be definite or deterministic. Section 14.4, the expectation value. Well, again, if you have a particle, you know its wave function psi. Let's say this psi is a linear combination of the eigenfunctions of a physical observable A. And then if you try to measure the value of A, you're not going to get a certain value. It's impossible. You will be able to get A1, A2, A3, A4, or some other eigenvalues. All right? But there's one thing we can do exactly. We can determine the weighted average of the value of A. The equation is here. So again, this psi is a combination of the eigenfunctions of the A operator. Okay? So if you apply this A to psi, you will not be able to get this psi back multiplied by a constant. Because again, this psi is not an eigenfunction of A. Alright? But however, you can determine the weighted average of A by evaluating these two integrals. On the bottom, it's just the integral of the squared modulus of psi. Remember, the squared modulus of psi is simply the complex conjugate of psi multiplied by psi. On top, it's a little tricky. You need to apply this operator, A, to psi first. Okay, you need to do this first. All right, you will generate a new function, and then you multiply this new function by psi star. All right, and then you integrate this product. In the end, you will be able to get the weighted average of A. Now, let me give you an example to explain weighted average. Again, if you buy a lottery ticket, let's say 1% chance you win $100, 99% chance you win nothing. What's the weighted average of your return? Well, it's 99% times 0 plus 1% times $100. So it's going to be $1. The weighted average is going to be $1 in this case. However, you will never actually get $1 as the outcome of buying one lottery ticket. Either you get $100 or you get nothing. You will never get $1. However, the weighted average is $1. Now let's look at this equation again. On the bottom, if psi is normalized, this integral is 1. If this integral is 1, we say psi is normalized. In that case, the average or the weighted average of A is simply the top integral. Now let me give you an example. In the hydrogen atom, you have one electron. In general chemistry, we learned this electron occupies the 1s orbital. In quantum mechanics, it's not necessarily true. And it can be a combination of the 1s orbital and 2s orbital, or 2px orbital and 3s orbital at the same time. We call this a superposition of the 1s orbital and 2s orbital, 2px orbital, and 3s orbital. So what's the energy of this electron? We don't know. If you try to measure the energy of the electron, you may get the energy of 1s or 2s or 2px or 3s orbitals. And if you try to again measure its energy, you will get all these possible values. Let's say if you get the energy for the 2s electron in your first measurement, after the first measurement, each successive measurement will generate the same energy. So if your first measurement is 3s, all successive measurements will give you 3s energy. If your first measurement is 2p, all successive measurement will give you the energy of 2p. Now let's assume these coefficients, B1, B2, B3, and B4, can normalize the wave function of the electron. So that means the sum of Bi squared is 1. Well, there's a reason behind this. You'll learn this a bit later. But if that's the case, we say the average energy of the electron or expectation energy, well, that's the term in quantum mechanics. The expectation energy is the weighted average energy. It's going to be the sum of the probability. So Bi squared is the probability times the energy of that eigenfunction. Now let me give you a more specific example. Let's say we have an electron in the hydrogen atom. It's a linear combination of this 1s wave function and 3p wave function. So if you ask me which orbital does this electron occupy, I say I don't know. It could be 1s orbital. It could be 3p orbital. Two possibilities. And then if you ask me about the probability, I will say 0.8 squared. That's 64% chance this electron is in the 1s orbital. 36% chance this electron is in the 3p orbital. I don't know what the energy is, but if you ask me about the expectation energy, well, I can do that. It's the probability, weighted energy. So this is the probability of finding the electron in the 1s orbital, 64%. And this is the energy of the 1s orbital, negative half. This is the probability of finding the electron in the 3p orbital. And this is the energy of the 3p orbital. So you do this calculations, you will get 64% times negative 1/2. This is the energy of the 1s orbital. You get negative 0.32. Over here, this is the probability. This is the energy of the 3p orbital. And together, you have the product, negative 0.32 and negative 0.02. So you put them together, you get negative 0.34. So really, I know the energy of the 1s orbital is negative 1/2. The energy of the 3p orbital is negative 1 over 18. So 1 over 18 is roughly negative 0.056. But the expectation value, well, it is neither negative 1/2 nor negative 1/18. It's negative 0.34. However, if you try to measure the energy of the electron, you will never get this negative 0.34. You will get either negative 1/2 or negative 1/18. If you have 100 such systems, okay, exactly the same, 100 such systems, okay, and you measure their energy, okay, around 64% of the time, around 64% of this 100 systems will give you this number. Around 36% of the systems will give you this number. Okay. Section 14.5, the evolution in time of a quantum mechanical system. So this is just the time-dependent Schrodinger equation. H psi is equal to I h bar times delta psi over delta t. This equation tells you how psi changes with time. So H is the Hamiltonian operator. The physical meaning of H is the total energy. Psi is the wave function of the system. I is the square root of negative 1. H bar is the reduced constant. H bar is h over 2 pi. And over here, this is simply the first derivative of psi with respect to time. Now, postulate 6. Wave functions describing a many electron system must change sign under the exchange of two electrons. Wave functions of electrons must be anti-symmetric with respect to the exchange of the coordinates, including the spin coordinates of two electrons. So what does this statement mean? Well, let's say we have two electrons, right? And we can use a wave function here to describe these two electrons. Okay? So R1 is the coordinates of electron 1, R2 is the coordinates of electron 2, T is time. And in this case, this R1 is not only the X, Y, Z coordinates of electron 1. It also includes the spin coordinates of electron 1. Remember, electrons spin, right? So we have a spin coordinate for every single electron. So in this R1 vector, there are 4 components: X1, Y1, Z1, and omega 1. Omega 1 is the spin coordinate of that electron. Now, if we swap the coordinates of electron 1 and electron 2, we get this R2 here, R1 here. So basically, whenever you see R1, you replace that with R2. And whenever you see R2, you replace that with R1 in this side. And then you get this function. So quantum mechanical postulate 6 states that if you swap electrons 1 and 2, the sign of the wave function must change. That means anti-symmetric. All right, that means anti-symmetric. If we're looking at a time-independent Schrodinger equation, and then we can drop time. All right. Now let's look at the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons can have the same set of quantum numbers. Right. This principle is the result of this anti-symmetry principle, or postulate 6. Again, no two electrons may occupy the same spatial orbital. Spatial orbital refers to a function of x, y, and z. No two electrons may occupy the same spatial orbital and have the same spin. So you can't have two alpha electrons occupy the same 1s orbital in hydrogen. We can prove this. Well, if two electrons may occupy the same spatial orbital and have the same spin, that means, well, they have exactly same coordinates. And these two electrons are indistinguishable. So supposedly, if we swap these two electrons, we should be able to get the same wave function. Because these two electrons, again, they behave exactly in the same way. That's why we can swap these two. All right, but from postulate 6, when we swap R2 and R1, we should change sign. All right, so you have negative sign here. So you compare this equation and this equation. The only difference is over here it's positive, but here it's negative. And that means this is equal to this. A function psi of R2 and R1 is equal to negative psi of R2 and R1. How is that possible? Ask yourself, if a function f is equal to negative f, what will happen? If f is equal to negative f, then f has to be 0. So if this psi of R2 and R1 is equal to negative psi of R2 and R1, that means psi R2, R1 is just 0. Negative psi R2, R1 is just 0. In that case, psi R1, R2 is also 0. So this wave function is 0. However, a wave function may not have any physical meaning. A wave function does not always have a physical meaning. Very often, it does not have a physical meaning at all, especially if you are looking at a wave function that contains imaginary numbers or imaginary functions. There's no meaning of imaginary numbers. You can't make a measurement of the position and say it's negative 2i meters. You can't measure its mass and tell me the mass is 5i kilometers. All right? But if you take the squared modulus of a wave function, it does have a physical meaning. The squared modulus of a wave function is the probability density. So now if a wave function is 0, we calculate its squared modulus. Well, it has to be 0. That means the probability density is 0. So our conclusion is this. The probability of finding two electrons with the same spin and occupy the same orbital is exactly 0. So over here, this is our conclusion. It's exactly 0. Again, this results in the Pauli exclusion principle. No two electrons may have the same set of quantum numbers. Well, if they did, we can calculate the probability density. It's exactly 0. Finally, quantum mechanical postulates 1, 2, 3, 4, 5, 6 build the foundation of the entire quantum chemistry. There's no way to prove these 6 postulates exactly. There's no way to prove them rigorously. Those are postulates. We will have to accept these 6 postulates blindly to study quantum chemistry. Let me give you another example. In thermodynamics, you learn this. Energy cannot be created or destroyed. You'll have to accept this first law of thermodynamics to study thermodynamics. All right, you cannot prove this first law exactly or rigorously. Just accept it. 14.6. Do superposition wave functions really exist? Yes, yes, yes. Please watch this video on some light quantum mechanics. So I have this video here. Over here, we have 3 filters to filter the light, polarized light. This is a fairly long video, 22-minute video, but I recommend you to watch the entire video to have a better understanding about the superposition of the wave functions and to have a better understanding of the 6 quantum mechanical postulates.